Efficiently removal of copper and cadmium from wastewater using activated carbon produced from Moringa oleifera bark. Abstract: Moringa oleifera is a multipurpose tree. The main aim of the study was to use the Moringa oleifera bark with low doses as an adsorbent for the maximum removal of copper, Cu, and cadmium, Cd, from wastewater. There are some vital parameters which influence adsorption process such as contact time, adsorbent dose, initial concentration, and pH were investigated. The activated carbon of Moringa oleifera bark with surface area of 439.2309 m superscript 2/G and pore volume of 0.189245 cm superscript 3/G was achieved at 700 degrees Celsius and used 10% zinc chloride and 0.5 m sulfuric acid as an activating agent to char ratio 5:1. The copper, Cu, was fully eliminated, 100%, from aqueous solution within 10 minutes, while cadmium, Cd, also was significantly removed using 0.25 gm/L of adsorbents. The Freundlich isotherm, pseudo second-order kinetic equations were well fitted with a correlation coefficient of 0.993 and 1, for copper and 0.953 and 0.999, for cadmium respectively. We observed that at pH 11, adsorbents showed maximum adsorption capacity. Therefore, it can be used as a potential, eco-friendly, non-toxic, cost-effective application for wastewater treatment. Finally, this works also focused regeneration of adsorbents using solvents for further highest reuse of it. Keywords: Moringa oleifera bark, activated carbon, adsorption, heavy metal, wastewater treatment. Introduction. Pure water has essential mineral elements which are very important for human beings and animals. Every cell of a live body needs pure water to continue normal activities. Pure fresh water does not appear in nature available due to contain huge contaminants in the environment. Many pollutants, especially inorganic in nature like heavy metal, contaminate water ecosystems and create serious problems. Toxic metal compounds contaminate not only surface water but also groundwater. Most of the heavy metal come from industry. Major toxic elements are lead, Pb, copper, Cu, nickel, Ni, cadmium, Cd, chromium, Cr, etc. Wastewater mainly comes from municipal, agricultural, and industrial activity. 1. Many heavy metals are released from paint, ceramics, and dyes industries too. According to WHO, 1997, any change in the physical, chemical, and biological properties of water may be dangerous effect on human beings and animals. This is known as water pollution. Polluted water contain various poisonous agents such as heavy metal, color, dyes, grease, oil and bacteria, etc. The presence of these agents in water system may cause various waterborne diseases. Human and animal use water for several purposes. But the water purity level is very crucial. For this reason, it can direct effect on health. The traditional wastewater treatment is used aluminium sulfate, alum, and calcium hypochlorite. But it's very costly for developing country. Wastewater is very harmful for human body and environment. 3. Cadmium, Cd, is released from zinc smelting, and paint sludge. Lead is released from lead batteries and ceramics. 4. Metal ions are being important pollutants due to their toxicity. 5. Toxic heavy metal is very dangerous for non-biodegradability. These all gather in living organism causes appear disease and sicknesses. 6. This poisonousness may influence at nervous systems and other vital organs. 7. There are several conventional methods like physical, biological, and chemical methods for eliminating heavy metal from wastewater. 8. 9. Adsorption is one of the vital process for toxic metal removal from wastewater. 10. Most of the water treatment processes are very costly in the global. 11. 12. Adsorption is a physico-chemical phenomenon which can adsorb contaminants from wastewater by surface chemistry of adsorbents. Normally, commercial activated carbon is used as adsorbent in adsorption process for the wastewater treatment due to high adsorption capacity and environmental friendly. 13. But it is very costly process. 14. Therefore, it is essential to find natural alternatives that is cost effective and available. Natural byproducts are the essential source for adsorbents. There are some polar functional groups. Most of the vital groups are hydroxyl, aldehydes, carboxylic, and ketones too. These groups can fix heavy metals by providing an electron pair. 5. Several agricultural waste like neem bark, Moringa oleifera bark, rice husk have binding capacity that adsorb pollutant from aqueous solution. Adsorption capacity can be developed using chemically activated adsorbents. Adsorption method is very popular for effectiveness, cheap and available every place. 15. Moringa oleifera, MO, is one of these alternatives for wastewater treatment. 16, 17. It has been found useful in nutrition, water purification, and industrial applications. It's also called drumstick or ben oil tree and is a medium-sized medicinal tree. It is available in South Asia, Africa, and South America. Leaves and seeds of MO are very frequently used for water treatment. 18. It has no side effects. It is non-toxic and ecological material. 19. MOCR, Moringa oleifera cake residue, don't need further preparation for water purification process. 20. MO seed has excellent coagulant properties to purify contaminated water. 21. It can remove turbidity from wastewater and also has antimicrobial properties. 22. Moringa oleifera bark have non-toxic natural organic polymers such as alkaloids, phenols, and glycosides which have been employed as an effective adsorbent for purification of wastewater. Many researchers have used Moringa oleifera seeds, leaves and fruits for water decontamination. The seeds of Moringa oleifera contain polyelectrolytes which can bind contaminants. Moringa oleifera have the valuable effect as medicine, nutrition, water management, and so on. 15. Leaves, fruits, roots of MO are used as vegetables. 23 and source of vitamins. 24, 25. Other sides, various parts of MO such as stem, bark, and roots have antimicrobial activities. 26, 27. Moringa oleifera leaves have both macro and micronutrients such as SS-carotene, protein etc. Its leaf possesses hypolipidemic and anti-atherosclerotic activities. 28. Moringa oleifera pods have free radical scavenging abilities. 29. Its act as a natural antioxidant. 30. Like some other plants which are reported as natural sources of antioxidants. 31, 32. Moringa oleifera bark also remove heavy metal like Ni2 from wastewater. 33. It has maximum adsorption capacity of 30.38 mg/g34. Moringa oleifera is a low-cost plant and biodegradable sludge. A central carbon atom of glucosinolate is bonded to thioglucose group with a sulfur atom and also bonded to a sulfate group with a nitrogen atom. These functional groups can be used to remove contaminants from wastewater. Finally, the major objective of this experiments was to use activated carbon of the Moringa oleifera bark with low doses as an adsorbent to successfully eliminate copper, Cu, and cadmium, Cd, from wastewater. 2. Experimental. A. Sample collection and preparation. Moringa oleifera bark were collected from natural sources near the University Sains Islam Malaysia, USIM, campus, in front of Acacia Park, Bandar Baru Nila, Negeri Sembilan, Malaysia, and washed with distilled water. The barks were sun-dried for 6 hours, then it washed with distilled water to remove dirt from its surface and dried in an oven at 110 degrees Celsius for 13 hours. The Moringa oleifera bark were reduced into smaller particle sizes using mortar and pestle as well as blinder. The samples, 100 g, were then chemically activated using 500 ml zinc chloride, 10% ZnCl2, and sulfuric acid, 0.5 mH2SO4, with ratio of 1:5 for 12 hours. Then the samples were dried in the oven at 110 degrees Celsius for 12 hours. It was grinded and sieved at 400 m. Then the sample was kept in the desiccator for further use. The precursor was placed in the furnace at 700 degrees Celsius with heating rate of 10 degrees C/min for 60 minutes. During the carbonization process, purified nitrogen was flown. It was cooled in normal temperature. This activated carbon samples were washed severally with distilled water. The washed samples were dried in oven at 110 degrees Celsius for 15 hours. These were then sieved with a sieve of 400 m. The activated carbon samples were kept in a polypropylene bottle to avoid moisture. These prepared activated carbon of Moringa oleifera bark were used for the experiments as the adsorbent in adsorption process. B Instrumentation. Water Distillatory, 2108, GLF, Germany, pH meter, 3510, Genway, Analytical Balance, CP 2245, Sartorius, USA, Oven, Furnace, Shaker and Blinder are used during the study. The concentration of before and after adsorption of solution were determined using atomic absorption spectrophotometer, AAS 240 FSA, USA. FTIR spectra were determined using Perkin-Elmer FTIR Model 1600, Greenville, South Carolina, USA, where the spectra were obtained ranging 4000-400 cm1. Microporosity of outer surface of adsorbents and pore size were obtained using scanning electron microscope, SEM Hitachi SU 6600, Tokyo, Japan, and Brunautoremitteller, Bet, Belsorp Mini, Chiba, Japan. See chemicals. Almost chemicals were of analytical grading and were directly used without further purification. The chemicals such as CuSO 4.5H2O, 99%, CD, NO3, 2.4 H2O, 99%, 0.5 MHCl, 70%, 0.5 MH2SO4, 98%, 0.5 MHNO3, 70%, 1 NNaOH, 0.05 M nano3 buffer, 10%. ZnCl2, were purchased from Merck, Germany. All chemicals were used as received. Adsorption experiments. Stock solution of metal were made by dissolving metal nitrate, CD, NO3, 2, and sulfate salts, CuSO4, in deionized water. Different concentrations were obtained from the stock solutions. This study was conducted by adding 0.25 gm/L activated carbon in solutions. Flask with adsorbents are placed in a shaker at room temperature, 25 plus or minus 2 degrees C, with 200 rpm speed for 2 hours. The pH was controlled at 11 using 0.1 N nano3 buffer solution to get best adsorption capacity for this experiment, but to observe the effect of pH of the solution were adjusted ranging from 2 to 12 by 0.1 N, HCl and NaOH, solutions. Then after 10, 20, 30, 60, and 120 minutes the samples were taken and filtered with Whitman filter paper. It was analyzed using atomic adsorption spectrophotometer, AAS. According to equation 1, the amount of adsorbate adsorbed on the adsorbent at equilibrium, QE, mg/g, was calculated and the percent removal of adsorbate was evaluated as expressed in equation 2, 35. Where Co and Ce, mg/L, are the concentrations of solution at initial and at equilibrium time, respectively. V is the volume of the solution, L, and W is the mass of adsorbent used, G. Adsorption isotherm and kinetics equation. The most commonly used adsorption isotherm models are those of Freundlich and Langmuir. In this work, Langmuir model was tested and given as where Qm equals Q for a complete monolayer, G adsorbate/G sorbate, Kq equals a coefficient, Kg/M3 or G/Cm3. Taking reciprocal and rearranging equation 3 gives a plot of 1/Q versus 1/C gives a straight line of slope 1/KQQM and an intercept of 1/QM. Equation 4 could be expressed in a standard format as given below, where Ce is the equilibrium concentration of sorbate, mg/liter or ppm or G/Cm3 or mol/M3, Qe is the amount adsorbed at equilibrium, mgg1, while Qo and B are the Langmuir constants related to capacity, mgg1, and energy respectively. A plot of Ce/Qe versus Ce gives a straight line of slope 1/O and intercept of 1/QB0. However, a pseudo first-order kinetic model as recommended by 6 is given as where Qe and Qt are adsorption capacity terms at equilibrium and at time t respectively, mg/g, K1 is the rate constant. Integrating equation 6 with the boundary conditions gives a plot of log Qe Qt versus t is a linear relationship from where K1 and Qe can be determined respectively. In a similar manner the pseudo second order model is expressed as where K2 is the pseudo second order rate constant of adsorption. After integration, the linearized form of equation 9 is again a plot of t/Qt versus t will give a linear relationship with 1/Qe and 1/2e2 as the slope and intercept respectively. 3. Result and discussion. Characterization of activated carbon. 1. Surface morphology. Figure 1a shows the FISM micrographs of the Moringa oleifera bark activated carbon before adsorption under 1000x magnification, while b is the micrographs of the activated carbon after adsorption under 30,000x magnifications. There were present many holes on its surface. These holes were the available pores, where copper and cadmium molecules were to be captured from wastewater solution. Large and well-developed pore were obtained from prepared activated carbon under optimum condition, at 700 degrees Celsius temperature, activation time 60 minute, as well as char, ZnCl2 and H2SO4 impregnation ratio 1:5. It might be occurred due to use chemically activity agent. The adsorbed metal molecules got to fill the pores from adsorbent surface to inner pore and at last it's bind at the available sites on their surface. Surface area and pore volume development could be happened also during pyrolysis process. This produced well-developed pore was the important factor to adsorb the maximum heavy metal from wastewater. Both micrographs presented with the morphological changes of the carbon materials during before and after adsorption processes. Figure 1, B, shows after adsorption most of the pore of activated carbon has been filled up by heavy metal. After carbonization was performed under inert condition, some irregular holes and pores were developed on the surfaces of the chars. This was due to the sudden burst of the thermal expansion from pyrolysis. Pore development in the char during pyrolysis was important, since it would develop the surface area and pore volume of the activated carbon after the activation process 36. The activated carbon formed irregular, large caved-in shaped cavities on its surface. The adsorption of cadmium at the surface of adsorbents might be physiosorption and copper could be occurred chemisorption. 2. Surface area and porosity. In this study, the surface area and porosity of the prepared activated carbon were analyzed. The BET surface areas were found to be relatively high. The smallest pore was surface area of 396.9325 m superscript 2/g and the largest was 435.1738 m superscript 2/g when pyrolysis was done at 700 degrees Celsius. The total pore volumes measured as higher for single point and micropore were 0.189245 cm3/g and 0.153732 cm3/g respectively. The development of more surface area and pores in activated carbon treated with acid solution is likely to be due to the elimination of impurities on the surface and/or in the pores. The pore size for single pore, diameter, and micropore, width, were analyzed as 68.488A and 17.234A. Activated carbon can consist of mineral matter up to 15% in the form of ash content, which clogs up in the pores, AGET.AL 2015. According to 37, the minerals are observed as unwanted contaminants such as N, P, Si, Na, K, Zn, and Fe. In order to purify the prepared activated carbon and to remove the contaminants, acid solution is usually used during washing part and in further treatment. These inorganic elements could be removed from activated carbon with acid, H2SO4 and ZnCl2, treatment in order to reduce the ash content. 3. Surface functional groups. The FTIR spectra analysis is essential to determine various surface function of Moringa oleifera bark, Mohd, as shown in Figure 2. The FTIR spectrum of Mohd shown broad peaks at 3371 cm1 which are attributed to the OH stretching band of hydroxyl group of phenols and alcohols in lignin and cellulose of Mohd before adsorption process 3839. The distinct peaks observed in 3183 cm1 are detected to the CH stretching vibrations of aliphatic hydrocarbons 40. The band at a range of 1615 to 1430 cm1 is attributed to C=C stretching vibrations, and the peak 900 cm1 results of CH, out of plane, confirm the presence of aromatic ring in the adsorbent 41. The peaks at 1126 cm1 may denote the presence of stretching CO, which includes compounds such as carboxyl groups that provide adsorption sites for the metal ions. Oxygen functional groups of ketone, C=O, was not detected in the prepared activated carbon. The presence of oxygen, CO, functional group peak was detected at 1126 cm1 on the surface of activated carbon. It was expected to indicate the polarity. After adsorption of heavy metal, peaks were detected with slightly shifting at 3500 cm1, OH, 1432 cm1, CO, 1123 cm1, CO, stretching, peak for 3125, CH, stretching due to bind with metal. B. Equilibrium studies. The equilibrium curve of copper and cadmium for the Moringa oleifera activated carbon was studied and shown in Figure 3. The copper curve shows a concave downward shape due to high affinity between absorbate and activated carbon. The contaminant metals were cationic form. The adsorption mechanism could be occurred by ion exchange or electrostatic forces due to possess oxygen-containing group, COOH, on surface of adsorbents. So, with increasing the oxygen-containing group of adsorbents, the quantity of adsorbate also increased. The amount of adsorbate ranged from 3.98 mg/g to 20.45 mg/g within 10 minutes for ranging initial concentration, 1 to 5, mg/L of copper salt solution were observed where final concentration obtained 0, Cf equals 0, and after 120 minutes the quantity of adsorbate ranged from 3.98 mg/G to 20.09 mg/G respectively. On contrast, for cadmium salt solution adsorbed amount were obtained from 4.36 mg/G to 19.65 mg/G at 10 minutes with final concentration as Cf0 and at equilibrium state the quantity of adsorbent shown 3.4 mg/G to 11.42 mg/G. Therefore, at 700 degrees Celsius activation temperature and char, zinc chloride and sulfuric acid with ratio 1:5, the activated carbon showed optimum adsorptive capacity. The results showed a rapid uptake of adsorbate molecules onto the surface of the adsorbent at the first 10 minutes, and then shown slight desorption and again a slower uptake up to 120 minutes. The reason for this behavior is that the adsorptive site becomes loaded as molecules adhere to the surface of the carbon structure. The values however greatly depend on the equilibrium concentration of the effluent with the adsorbent. See Langmuir and Freundlich isotherms. Langmuir isotherm expressed monolayer of the metal ions are designed on adsorbent. The experimental Qmax for Moringa oleifera are found to be 20.43 and 17.01 for Cu and Cd, comparable with theoretically calculated Qmax as given in Table 1. The higher value of B is described the affinity of the adsorbent to adsorb metal ions. The value of Qmax can also be considered as the total number of active sites of adsorbents for adsorption. According to the Table 1, the affinity order of Moringa oleifera is like CuCd. From the plot of log Q against log Ce were obtained the constant K and 1/Nk is indicated the strength of adsorption. Lower value of K designates the more adsorption 42. Another constant 1/N is indicated the adsorption intensity. Data would be favorable when N value is 1N10. All data of Moringa oleifera are well fitted of Langmuir isotherm and Freundlich isotherm. The mean adsorption energy, E, can describe about adsorption properties. It can be calculated from the Dr isotherm model 43. If the values of E 8 kJ mol1, it follows physical adsorption. When the value of E is ranging 8 to 16, it follows chemical adsorption. From the Table 1 of adsorption energy values suggested that Moringa oleifera indicates a physical adsorption for cadmium, Cd, E equals 2.61, metal ions and copper, Cu, E equals 9.8, adsorbed by chemical adsorption process. The experimental data were well fitted into Freundlich isotherm and represented in figures 5. For Langmuir isotherm, plot of Ce/QE against Ce shown linear relationship with R2 equals 0.989 of copper and R2 equals 0.801 of cadmium. For Freundlich isotherm, plot of log QE against log Ce gave also linear relationship with R2 equals 0.993 of copper and R2 equals 0.953 of cadmium. The Freundlich plot and the Langmuir plot fitted favorably well with the isotherms because the value of RL obtained from slope were 0.0021 for copper and 0.22 for cadmium, favorable when 0 RL1. For Freundlich isotherm, a value of N, 4.22, 1 for copper and 1.91 greater than 1 for cadmium, favorable when 1N10, obtained represents a favorable condition following the works of McKay and Ho, 1998. D. Adsorption kinetic studies. The correlation coefficient, rate constants, calculated metal uptake and other kinetic constant from the three models studied were shown in Table 2. These calculated kinetic constants indicated pseudo second order kinetic with highest correlation coefficient R2 to fit best. Kinetic does not apply to pseudo first order and interparticle diffusion model. Equally, calculated metal uptake in pseudo first order kinetic is by far less than one obtained from experiment, QE, cal, QE, EXP. Whereas, in pseudo second order kinetic, the metal uptake calculated is closer to that obtained from experiment. This further confirms fitness of kinetic studies with pseudo second order. If the linearity was achieved and the line passes through the origin, it indicates the internal diffusion is the slowest step in the adsorption process. From Figure 6, graph line for copper and cadmium of Moringa oleifera were not linearity and did not pass through the origin. It is indicated that the adsorption process was controlled by film diffusion 44. From the figures 7 and 8 of this finding, the pseudo-second order well favored the adsorption process with a regression correlation R2 of 1 for copper and 0.999 for cadmium, while the pseudo-first order kinetic coefficient R2 got 0.963 for copper and 0.864 for cadmium. The correlation coefficient was well fitted for pseudo second-order contrast of first-order and interparticle diffusion. Therefore, the adsorption and kinetics of Cu2+ ions and Cd2+ could be well approximated adequately by the second-order model. The effect of initial concentration. The effect of initial concentration for the removal of copper and cadmium from wastewater using activated carbon of Moringa oleifera shown as figure 9. The initial concentrations were set at 1, 2, 3, 5 mg/L. It may be described from the graph that with increasing the initial concentration, the removal percentage of copper and cadmium from aqueous solution were decreased, but the adsorption capacity of both metals also was increased using all activated carbon. Within 10 minutes for all initial concentration, mg/L, absolutely, 100% of copper was removed and the adsorption quantity was 20.45 mg/G, but after 120 minutes at equilibrium copper removal percentage was slightly decreased and obtained more than 98% as shown in table 3. On contrast, the removal percentage of cadmium were 100% for concentration of 1 and 2 mg/L and more than 96% for concentration of 5 mg/L in just 10 minutes, but after equilibrium, the removal percentage of cadmium was decreased and obtained more than 56. This type of pattern suggested that it can be possible due to monolayer formation of pollutant on the adsorbent surface. 45. F. Effect of adsorption time. The adsorption experiments were necessary to define the contact time essential to touch the equilibrium position. The adsorption performance of copper and cadmium were conducted at time intervals 10 to 120 minutes as shown in figure 10. Firstly, the amount of metal uptake was very good from 10 minutes to equilibrium state for copper, but for cadmium after 10 minutes was decreased, then steady with time till equilibrium state. After 120 minutes it was reached at equilibrium state where metal cannot be removed from solution more. The quick uptake happened was due to more active sites on Moringa oleifera bark were open. It permitted rapidly binding pollutant on the adsorbents. Since the active part became used, the adsorption rates fall down. It can be occurred for reducing active part by metal ions. The elimination activity reduced by about 2 to 40% with increasing contact time to reach equilibrium position. It caused from saturation of adsorbent surface with heavy metals followed by adsorption and desorption process after saturation. 43. G. Effect of adsorbent dosage. The effect of adsorbent dosage was carried out ranging from 5 mg to 50 mg of each activated carbon during removal of heavy metal adsorption from 100 ml aqueous solution as shown in figure 11. This figure shows that with increasing the adsorbent dosage, the removal of metal ion also improved from 20% to 100% for copper and 56% for cadmium. After reaching at 0.025 g of adsorbent dosage, the adsorption process also reached equilibrium state. The removal percentage of pollutant improved from aqueous solution with the improving dosage. This can be obtained to have available active part of adsorbents for complexation of heavy metal. Further increasing the adsorbent dose cannot show significant improvement in removal adsorption. This may be occurred due to reach the equilibrium state between binding adsorbate and unabsorbed adsorbate in adsorption process. H. Effect of pH. The adsorption performance of activated carbon can affect by pH of solution. 46. This study's removal percentage of both metals were conducted ranging pH 2 to 12 of solution, as shown in figure 12. The graph shows that with increasing the pH values, the metal removal percentage also increased and at pH 11 maximum removal percentage obtained. If the pH value was low, the outer surface of adsorbents was gathered with many positive charges, which provided a greater static repulsion force. If pH increased, the static repulsion forces reduced, and heavy metal adsorption improved. When the pH value less than 8, the dominant species CD2 exists CD2+. At the pH range of 9 to 11, CD2 mainly exists in the cationic form of CD4, O, 44+. On the other hand, at pH above the 11, CD2 is in the form of CD, O2. The technique of cadmium, 2, in adsorption can be conducted by the electrostatic forces. With the increasing the pH value, the concentration of H+ ion in solution decreases, the negative surface charge will be an increase on the activated carbon above the pH, pZc, value of 5.4. For this reason, to attract of adsorbing metal cations mainly in the cationic form CD4+, and they more easily get adsorbed onto the adsorbents. The CD2 adsorption on activated carbon can be also described by ion exchange mechanism. The main functional groups on the surface of adsorbents are the carboxyl, hydroxyl, methoxyl group, which are responsible for ion exchange onto their surface. The mechanism taking place on adsorbents is shown in equation. 4COOH plus CD4 plus equals dash, 2, Cu, 2CD4 plus 4H plus. At lower pH less than 5, Cu, 2, mainly exits as Cu2 plus, but at higher pH range of 7 to 11 the predominant species of Cu, 2, is Cu3, O, 42 plus. At around a pH of 6 there is a very small fraction of Cu2, O, 22 plus present in the solution. The higher adsorption rate for Moringa oleifera activated carbon at a pH 11 can be explained by the mechanism of electrostatic force. At pH PZC, 5.4 for adsorbents, the surface of adsorbent is negatively charged, which carry on an electrostatic force between the metal cation Cu3, O, 42 plus and active sites of adsorbent. At a lower pH, the adsorbent surface contains positively charged and H plus ion in the solution inhibit the approach the metal cations and less adsorption occur. On the other hand, the acidic carboxylic group on surface of adsorbents can conduct adsorption of metal ions by ion exchange mechanism, which is shown in equation below. At pH 2, the metal adsorption was lower due to present available H plus ions. This H plus ions contested with metal ions for the active sites, hampering to adsorb of Cu2 plus and Cd2 plus ions with activated carbon. Protonated active part was not capable to adsorb metal due to electrostatic repulsion. As the pH increased, H plus ions decreased. Therefore, huge negatively charged sites were prepared and metal ions uptake increased by electrostatic attraction. Desorption of heavy metals. The reusability of Moringa oleifera was studied by cycling adsorption/desorption process, Co equals 5 mg/L, pH 11, S/L equals 0.25 gL1 and T equals 60 minute, T equals 250 C. The studies were conducted by batch desorption technique using HCl, H2SO4, NaOH and Na2CO3 of 0.1 N with the metal-loaded adsorbent, as shown in Figure 13 and Table 4. Hydrochloric acid performed great desorption efficacy for Cu, 2, 88.26%, and Cd, 2, 99.13%. After every adsorption run, activated carbon of Moringa oleifera was separated from the solution by filtration with Whitman filter paper and washed with distilled water. It was then dispersed in a solvent, HCl, shaken, 200 rpm, for 1 hour and washed with distilled water, then dried. Generally, with increasing cycle number, desorption efficiency decreases due to the reduced of adsorption capability as shown in Figure 14 and Table 5. In every cycle, innovative binding sites was decreased, which was generated by dilute HCl treatment. Desorption efficiency of Moringa oleifera was calculated from equation 14, where Qd is the mass of the metal ions, mg/g, desorbed from adsorbents, as well as Qe is the mass of metal ion, mg/g, adsorbed onto the adsorbents. The mass of metal ion desorbed, Qd, mg/g, is evaluated from this equation, where Cd is the concentration of the metal ion, mg/L, left in solution after desorption. The total volume, L, of the solution expressed Vd and W is the mass, G, of the adsorbent. Conclusion. The activated carbon from Moringa oleifera is an effective adsorbent for eliminating toxic metals from wastewater. The adsorptive capacity of the developed carbon depends on the activation process, which has impacts on pore size, pore volume, and surface area. The adsorption capacity of 20.09 mg/g for copper and 11.42 mg/g for cadmium were achieved using activated carbon of Moringa oleifera bark with an acid concentration of 0.5 mH2SO4. It showed that Cu was 100% removed from solution within 10 minutes and Cd also removed 96.32% from produced wastewater. From the isotherm plot, it was observed that Freundlich plot well fitted with generated data. A pseudo second-order isotherm with a regression correlation R2 of 1 for Cu and 0.999 of Cd were well achieved, as in contrast to first-order model of 0.963 Cu and 0.864 Cd. Therefore, a pseudo second-order kinetic model is preferred to pseudo first-order model for the kinetics of sorption for Cu2 plus and Cd2 plus adsorption. The carbon with higher pore volume and surface area was found to be more effective in removing these heavy metal ions. This plant has various chemical constituents. It also has the biological activities including the depletion of metal concentration. Moringa oleifera bark contain the antioxidant properties that are effective to reduce the oxidative stress induced by heavy metal. It was therefore concluded that Moringa oleifera bark acts as a well adsorbent for the treatment of wastewater and reuse it. This should be an encouragement for developing countries. Acknowledgement S. This research was partially supported by Universitas Sains Islam Malaysia.